Okay, this is going to be so quick because I'm pushing it. I'm so pressed for time. I'm supposed to be somewhere at 3, but I just wanted to just give this intro. So we're going to look into what I had mentioned before on one of my rants that I did. So we're going to look into time travel. And we're going to look into how it's possible, how it's been seen to be possible. We're going to get together and kick around the idea and the theory of time travel. But first, we have to look at the groundwork. We're going to take a look at the particle collider in CERN, the Large Hadron Collider. We're going to look at thermodynamics, thermogenics. Okay. Entropy, all this really good stuff that we're going to look at. So entropy is part of thermodynamics. So I guess before I get on the road, I'm home right now and I have to be somewhere at 3. And it's going to be 30 minutes away and I'm already going to be late. So let me just start off really quickly. Peace to everybody. I love you very much to the audience. But let me just start out talking to you about, we're going to go to CERN. Yes, I know a lot of you know about CERN, but we're going to look in on CERN, see what they're doing. So I just want to do the basics and quickly read a little bit of this article, just, talking about CERN and the particle collider and temperature. We want to really focus in all of this on temperature and energy. Okay, energy and temperature. In even though they are distinct from each other, they do correlate a lot of times. So we're going to really look at that as far as, and believe it or not, that fits into the idea of time travel, right? It does. Okay, so let me go ahead and read this. I'm going to screen share. I'm not going to be up here long, like I said, but I just want to get some information out because I've been wanting to do this for a while. And then it'll be, cutting it close and I'll say, oh, I'll do it later. So I just want to get something out. So this is really basic. This is the website. You can read about CERN anywhere. I'm talking about CERN in Switzerland, the Large Hadron Collider. But this is a website called Space. And let's just read a little bit about CERN, if I can just go fast. The Large Hadron Collider inside CERN's atom smasher. The Large Hadron Collider is the biggest and most powerful particle accelerator in the world. It is, and by the way, this is what, I just want to stop right for a second. I know I always do this, but listen. Now, when you have these very uninformed people calling you pseudo, you can go and show them actual exciting, innovative, groundbreaking, almost phenomenal science that is taking place right now while they're just locked in a box. You can go and look at the really exciting science, like talking about particle collision and time travel and pushing pushing your mind further as far as what we can do as far as thermodynamics and even thermogenics. The energy within your own body, how you produce energy. This is so crazy. We're going to talk about spontaneous human combustion, y'all, but not right now. So let me get back to reading about this, about the Hadron Collider, and then we'll talk more about the human combustion later. All right, let's get back on track, Nepal. European, okay, it's located in Switzerland. We already know that. The Large Hadron Collider restarted April 22nd, 2022. It was down for a minute for 3 years for maintenance work running through this. Scientists used the LHC, Large Hadron Collider, to test theoretical predictions in particle physics, particularly those associated with the Standard Model. While the Standard Model can explain almost all results, in particular, physics. Hold on, y'all. Just a second. Something happened here. Let me see here. What am I doing? Can you guys hear me? Whew, I thought I was muted. I had to double check. Okay. All right. Let me go back. I've done that before. Oh, let me go back to the article. All right. Sorry. Okay. So we know it's in Switzerland. Let's look at the measurements of it. I'll come back and go more in detail on it, but I just want to really quickly run through this. The LHC can reproduce the conditions that exist within a billionth of a second of the Big Bang. Isn't that amazing? The colossal accelerator allows scientists to collide high energy subatomic particles in a controlled environment and observe the interactions once they do so, right? One of the most significant LHC breakthroughs was in 2012, Higgs boson. Yes, we know about that, the God particle. Okay, going forward, I want to read something. A recent example occurred in January 2022 when CERN scientists announced evidence of X particles in the quark gluon plasma. Keep that in mind, right? The part that says quark gluon plasma, you're going to hear that a lot, produced in the Large Hadron Collider. Hiding behind the techno-speak is the eye-popping fact that CERN succeeded in recreating a situation that hasn't occurred naturally since a few microseconds after the Big Bang. That just happened in 2022. Okay, so when run 3, this is the run 3 that they're talking about. When run 3 commences, or actually, I think it already started, which this is just an old article. So they're saying they're gonna do a third run. This is a past article, so I think they already did it, but let me keep reading. When run 3 commences, we can expect a whole new spate of discoveries. So it's a good time to take a closer look at what makes the Large Hadron Collider and the rest of CERN so unique. And that's what we're doing. We're taking a closer look. Let me close this. So what's the Large Hadron Collider? All right, so the LHC is a particle accelerator, a device that boosts subatomic particles to enormous energies in a controlled way so that scientists can study the resulting interactions. And guess what? The Large Hadron Collider, that would the experiments that are taking place in there, it's the highest level of energy on the face of the earth. Wrap your mind around that. And we can convert that into temperatures if you're looking at plasma physics, you know, because what we said earlier when they said about glue, let me go back and read it for you, because when I get really into something, I start not making sense. In the quark gluon plasma, the part that they said the evidence of X particles in the quark gluon plasma. So when we convert the energy, the measurement of energy, which is phenomenal levels of energy going on in this Hadron Collider, I really want you to stop and think about this. On the face of the earth, in the Hadron Collider, is the highest level of energy, highest, so you could say the highest temperature when you're talking about in terms of plasma, right? Plasma physics, the highest temperature on the face of the earth, right? So why am I pushing temperature? Because there's going to be, when you think of energy, a lot of times you also want to think of temperature, all right? And the reason is, I know this is going to sound crazy, but I got to say it. When we're thinking about time travel and what we want to do is like say, okay, how can we actually get to the highest temperature, right? The highest energetic level to be able to convert ourselves to some other type of, our particles to something else to where we can actually move through time. It sounds like science fiction, but it isn't. It's actually real science. Now, let me keep reading about the Hadron Collider a little bit, but I want to go down and let you know how large it is and then tell you a little bit more specifically about the amount of energy that's going on in this Hadron Collider. Okay, the LHC is far but the biggest accelerator in the world. There are many accelerators, by the way, but the one in CERN is the biggest in the world, right? It occupies a circular tunnel nearly 17 miles, 27 kilometers in circumference. The middle letter H stands for hadron, and that's a generic term for composite LHC particles such as protons. All right, so what they're colliding are these hadrons, these particles. They're colliding them, right? Such as protons. Protons are basically light, right? Just letting you know that. All right, and let's see. Protons that are made up of smaller particles called quarks. Finally, the C stands for collider. The LHC accelerates two particles beams in opposite directions and all the action takes place when the beams collide. Like all physics, it's really that simple. It seems so like complex, but it's that simple. They're just like, let's smash some stuff up. Not that simple, but you get what I'm saying? Like all physics experiments, the LHC aims to test theoretical predictions. In this case, the so-called standard model of particle physics, and see if there are any holes in them. Why? Because physicists want to find a few holes in the standard model to be able to make sense of dark matter and dark energy, which they have no clue of what it is right now. Okay, fast forwarding, because I want to show you the energy, like read to you. Where is it? Oh, here it is. Okay, what to expect. Oh my gosh, I got to get it going. Okay, in the LHC, with the new upgrades, CERN has increased the power, listen to this, family, of the LHC's injectors. They feed the beams of accelerated particles into the collider, okay? At the time of the previous shutdown in 2018, the collider could accelerate beams up to an energy of 6.5 tera electron volts. That's phenomenal. I mean, it's not phenomenal. It's actually real. It's happening, but it's outstanding. And that value has been raised to 6.8 tera electron volts. Okay. So for reference, a single tera electron volt is equivalent to 1 trillion electron volts. An electron volt is a unit of energy. It is equivalent to the work done on an electron accelerating through the potential of 1 volt. Okay, so let me stop screen sharing this. And I want to go and show you in terms of like kelvins, which is a measurement of temperature, like energy / temperature, really temperature, and in like chemistry. And then I'll show you from kelvins to what we are familiar with, Fahrenheit. Okay, so let me find it. Here it is. It's just a quick Google search. So let me stop sharing this one. This is the most I'm going to have to be able to do right now. I can't go into like anything else until I get back, but let me screen share this just to give you the foundation. And then maybe while I'm on my drive, I will just give you some background of why I'm really showing you, laying the foundation of the Hadron Collider, the level of energy there in the Hadron Collider, and correlate this to obviously thermodynamics and even thermogenics, which would also let us, go into something fun like spontaneous human combustion. Yes, it's real. It is real. Okay, let's see. Let me see here. Is this it? Yeah, I just want to show you this quick Google search. So we saw electron volt, right? So what is the temperature of an electron volt? Obviously, the electron volt it's not literally a temperature, but this information, I put that information in to show you something. So an electron volt is a unit of energy, not a temperature. We know this, right? It is the amount of kinetic energy, which is, put a pin in kinetic energy, put a pin in that, write it down. That's going to be important because then we're going to look at velocity. Velocity and kinetic energy go hand in hand. They work. They work together. I'll go into detail about that later. But why am I saying put a pin in it? Because when we look at velocity, velocity is measured by time. It's measured by time, and kinetic energy is linked to velocity. So I digress. So it's the amount of kinetic energy gained by a single electron accelerating from rest through an electric potential difference of 1 volt in a vacuum. That's the Hadron Collider. We know that, right? So let's go down to this paragraph where it says, however, it says it's not a temperature. However, in certain fields, such as plasma physics, we were just looking at something about plasma when we're looking at the Hadron Collider, right? In certain fields of plasma physics, it is convenient to use electron volt to express temperature. And in that case, the electron volt is divided by the Boltzmann constant. You'll see that a lot. The Boltzmann constant will be also, when we speak about entropy, later on we will talk about entropy and relate that to Boltzmann, the physicist who has created theories on entropy. Anyway, the electron volt is divided by the Boltzmann constant to convert to the Kelvin scale. So in that case, they show you the formula to convert an electron volt. Stay with me. I'm about to wrap this up. To convert an electron volt, an electron volt to Kelvin, which is the measurement of temperature in chemistry. And then I'm going to show you a conversion from Kelvin to Fahrenheit so you can get an idea. So Kelvin, an electron volt, one electron volt, only one, is 11,604 and 5100ths Kelvin. 11,604.51 Kelvin. That's one electron volt. We're talking about tera electron volts when we look at the Hadron Collider, right? So that's Kelvin. And then when we look at, there's so much I wanted to go through, but okay, let me see. Where is it? When we look at, we're going to convert Kelvin to Fahrenheit. This is just for when people say shits and giggles, but not really. It's important so you can really conceptualize this better. So let's see. So we saw Kelvin. One electron volt is like almost 12,000 Kelvin, right? So let me share screen and show you how many Kelvin equal Fahrenheit. So as you see, 1 Kelvin is equal to 1.8 degrees Fahrenheit. So 1 Kelvin is equal to negative 457.87 hundredths Fahrenheit. To convert Kelvin to Fahrenheit, you can use the following. Fahrenheit equals Kelvin minus 273 and 15 hundredths times 9 divided by 5 plus 32. All right. Anyway, they did all the work for us. So 1.8 degrees Fahrenheit equals 1 Kelvin. Why is that important? Well, because I'll stop screen sharing, right? So if we take 1.8 degrees Fahrenheit, right? We know we're familiar with Fahrenheit. We're very familiar in the West, Fahrenheit. So we're going to take 1.8 degrees Fahrenheit. Oh, come on, calculator. 1.8 degrees Fahrenheit times, I forgot what that was with the Kelvin. Let me go back. The Kelvin times 11,604.5182. That is 20,888 and 13 hundredths degrees Fahrenheit. So almost 21,000 degrees Fahrenheit. Wow, that's crazy, right? And that's pretty much, I'm going to end it on that. And you might say, well, what was all that? Just get to the point. Oh my God, black plumber. Okay. Anyway, that was the point. The point is we're laying the groundwork so you can understand what we're dealing with as far as energy and temperature and how it all relates back to energy and temperature when we start talking about time travel. Not all of it is only time energy, but time travel, a huge part of time travel is when we wrap our minds around energy. And that's great, right? Because energy is something we can examine. Energy is something that we can definitely look into. And time travel is already taking place. I mean, it's already possible. It's already been proven that at different levels of elevation on the face of the earth, time moves slower. I believe, I always mix it up. Time moves slower the closer you are to the gravitational pull. So time moves slower when you're on the earth, when you're on actually ground level, than it would if you're elevated higher, above sea level, so to speak. So that's the point, black plumber. Okay. And so, all right, guys, I'm going to leave it at that. But the title, Thermodynamics, CERN, the Large Hadron Collider, Thermogenics. I didn't even get into Thermogenics yet. And people say, well, how does Thermogenics tie into that? I mean, that's about calories and, you know, building, increasing your metabolism. Yes, but remember, it's all energy. It all goes back to energy. Okay, super exciting. And then you'll be able to see things like, oh, okay, that makes sense. why, you know, light does certain things this way. And they say this. By the way, at CERN, there's an article, I can't read it right now, but I have it queued up. Experiments, obviously, collisions done with photons, they are actually at CERN creating matter out of light. Get out of here. This is exciting. It's not pseudo. So peace and love to the family. I don't know what Sonnetter has planned for tonight on the Sonnetter Studios channel, but I got to come back and do the rest of this. I can't just leave you hanging. However, I would be remiss if I closed out this stream without letting you know that we have an upcoming debate. If you haven't been around, and the debate is going to be who? Well, let's see here. It is Dr. Richard Carrier versus Jabari, Brother Jabari, Himnecher Jabari. In the toughest environment, is Christianity crafted out of the Kemetic myth? Is it? Well, we're going to find out who will prove their point best on December 23rd, 2023. That is just on Saturday. That's in a few days. 6 p.m. Eastern Standard Time. Get your ticket. It's $30 donation. You know, it's the season. You know what I'm saying? You can indulge. Do something good for yourself. I know everybody's running around doing so much, but yes, go to the debate. Get your tickets. The link. Let me see. The link should be in the description box. I really got to get on the road. But anyway, if you need the link, somebody please, Ahmad, if you could drop it for me quickly. If you're not in there, that's fine. You can always go to Sonnetter's channel. I'm pretty sure the link is in the description box, but you can go to the Sonnetter Studios channel and go to the description box and it will be there. Peace and love to the darkest minds of the light. I forgot to say that. Assalamu alaikum. Hotep, namaste, Jumbo, shalom, ashe, duantur. What else? All the greetings of love and light to the darkest minds of the light. I hope you like this so far. It's interesting. Maybe to get your mind rolling like, yeah, energy. Oh, and by the way, spontaneous human combustion is proven by a biogenesis. I think what is he? He says he's a biologist or something. He's a biologist. He's a biologist. Let me just throw this out here for you. I don't want to leave you hanging. You can do your research before I get back. Brian J. Ford. Yeah, he's a biologist. Brian J. Ford is going to talk to us. He has all kinds of research on spontaneous human combustion. That's what we will talk about. And then we're going to tie it all together. It's going to come all together. And we're going to talk about time travel. Yes, time travel. All right, peace. And to those out there saying pseudo, eat your hearts out, because we're over here. We are the deepest, darkest minds of the light. And we know how to use science and tie it into what people can think of that people can't even imagine, actually. People can't even wrap their minds around it. But we are wrapping our minds around things that people think are impossible. And mainstream science will help us do that. All right. Peace.